Over to you, Andy.
Thanks. Okay, so unlike some of the previous speakers, my demo actually does work on a Mac because it's just to hold up a DIMM. And yesterday, since I'm from Intel, I kind of have to say something about this. Yesterday, the 3D Crosspoint DIMM, the Intel 3D Crosspoint DIMM, had its first public demonstration. It was at the SAP trade show, or whatever their show is called, Sapphire. So if you Google that, you can probably read about it. But now you've all gotten to see the DIMM. And okay, so I'm Andy Rudoff. I work at Intel. I'm a non-volatile memory software architect. I put a picture of the DIMM on here that I got from marketing. And I, believe it or not, marketing actually put the banana for scale next to it. So I had to use both. I almost cropped out the banana, and I thought, I actually really like the way that looks. So now you can see the full-blown picture of this. Now, in a longer version of this talk, I'd start out by telling you why we care about persistent memory. But this is really a talk about what the current state of the ecosystem is. So I'll just summarize a few points rather than go through a bunch of slides that I don't have time for. But the promise of these emerging products like this one are, first of all, their capacity, right? So what Intel has said publicly is that they expect the capacity to be up to 3 terabytes per socket. So 2-socket systems are the most common servers in the world. Not for you guys, because you're probably HPC guys and you use bigger systems, but even so, yeah, that means 6 terabytes of memory. Right now, I don't even know if you can put 6 terabytes on a 2-socket system, but it would certainly be very expensive. So cheaper than DRAM is the second promise of these emerging technologies. And then obviously faster, so latencies of a hard drive measured in milliseconds, latency of a SSD measured in microseconds, latency of persistent memory measured in nanoseconds. So now we're starting to get closer to those DRAM speeds, and that's why there's so much excitement about it. But really, what's wrong with just plugging this stuff into existing systems? Why did we have to do anything in the ecosystem? And to really capture that, I grabbed this slide from IDF last year, and the IDF slide here is showing you the latency. So if I just want to go grab a few bytes off of persistence, right? This is how long it takes for me to get it off of an SSD. This is a NAND SSD. Actually, a SATA or a SAS SSD would be quite a bit higher over here. I didn't bother to put that on here. This is a modern NAND SSD that speaks NVM Express. That means it's a PCIe card. And so you can see the whole thing takes, 90 microseconds or so. And I've tried to divide up where that latency is spent into a couple of categories. The big blue category here, that's the media. That's how fast you can get something off of NAND, right? So down here is the driver stack, the file system and stuff like that, and it's just these couple of stripes here. And so if I went and did some work to make the file system twice as fast, you'd hardly notice it, right? Because really, this is the bulk of the work here. And these storage stacks are actually pretty fast. So there's really not a reason to worry about optimizing the software part of the path, because it's really a very small part of the path. Okay, so now Intel makes this stuff called 3D Crosspoint, and they've started shipping it in an SSD. It's called an Optane drive. It's also an NVM Express drive. It goes in the PCIe bus. And so I put up the same latency diagram here, and you can see the media time shrank way down. Right now the blue thing is pretty small now. And actually now the software stripes are starting to look kind of more significant. Right? So now maybe it does make sense for us to try and do something about the amount of time software is taking. It's more than half the latency now, right? So now it's starting to get interesting. So that's the idea. That's just why we took this same media and we put it on a DIMM. Now you get this picture over on the right where to read 64 bytes, you can see it's just this little sliver here. And we put it on a DIMM, so you read it with load instructions, not by going through a stack, not by going through a driver. So you can see it's actually, kind of a striking difference. If I only need 64 bytes and I do a read, that's how long it takes. Here, I don't have a choice. I have to read blocks because these are block-oriented devices. I can't read just 64 bytes. But if just for an apples-to-apples comparison, you can see if I read the entire 4K, I also put a little blob there so you can see about how long that takes. So that's why this is interesting. That's why we're doing something to the ecosystem. We have to get rid of these layers of software and figure out how to use this stuff directly as load store memory in order to really exploit what it can do. Okay, so how hard is that? You know, are we talking about you know, learning a new programming language or something? So I took this example off of our GitHub area. The URL's down at the bottom. These slides will be on the MSST website, so you can go play with this stuff if you want. If you're a Java programmer, you might recognize one of the common Java classes. It's called a sorted map. And we have a new version of it called the persistent sorted map. It works just like sorted map. You might recognize this API where I'm just doing a put here to set some element in the map. It's Java, it looks like Java, it's garbage collected, but it's persistent, right? And for the details of how you reconnect back up with it and everything, just go take a look at the repo. It's too long for this talk, but the point is that it's very simple. There's no cache flushing or magic transactions and things like this you have to worry about. The put is transactional in our persistent version of it. If the system crashes in the middle of this call, it either happened or it didn't happen, right? The Java library just basically handles it all. So, well, piece of cake, we're done, right? What is there more to do? Well, how did we get here, right? How did we get from me swinging this DIMM around here from persistent memory to this very high level language support? Okay, what's in between there? What's in between there are support for the programming models that people build on to get us here. And that's really what I'm here to talk about. Now, when I started this thing, looking at this, we formed a little group in SNIA. We all got together about it. We called it the NVM technical work group, the NVM programming technical work group, the SNIA twig. I'm pointing at the guy with the SNIA shirt over there just so that you can see him waving. And you know, back then we thought, oh, we need a programming model. But what I really realized is that when you walk up to somebody, your average engineer, and you say the word programming model, they might not think the same thing that you're thinking. In fact, I think there's at least 4 meanings of this term, programming model. One is, what's the interface between hardware and software, right? If I go buy a NIC, a networking card, the programming model is how software talks to it, right? So that's one meaning. But you know, I come from a processor company. Another meaning is, what are the instructions that you use to program to this thing, to get it to do things? Or how is the hardware exposed by the operating system up to applications? That's a third meaning of programming model. And then finally, somebody might just be, well, I'm just a software guy. I just want to know what the programming environment is. That's my programming model. You know, what are my APIs? What compilers should I be using? Things like that. So let's kind of quickly go through these 4 things, because some of them are very easy. First of all, obviously, the programming model for this is the same as any memory because it fits into the memory bus, right? So the result is that you access it like memory, it's cache coherent, you do loads and stores to it. If I store something to this, all the other processors see it because, like I say, it's cache coherent. And because it's part of the cache hierarchy, things like DMA, when you can receive a packet from the network right into your persistence, that works. Things like RDMA work. So that's pretty exciting. We'll talk more about that in a minute. So really, at this level, all we had to do to enable it was to make sure the OS knew about it. And to do that, we added some tables to the ACPI standard for x86 in 6.0. Actually, ACPI 6.2 is about to come out within literally days. And so that's been enhanced a couple times. But starting with ACPI 6.0, there's a table that communicates that you have persistent memory in your system. So that part of the ecosystem is basically done, and done through a standards body. Okay, my next meaning of programming model is the instruction set architecture. So the first thing you have to do is say, well, for your platform, where is the persistence domain? At what point after I do a store instruction, on x86 store instructions are called move, right? At what point after I do a store instruction do I know that the data is persistent? So on x86 platforms, we say if you make it to out of the CPU caches where the store gets accepted by the memory subsystem, then it's persistent. Okay? In other words, there are hardware mechanisms to make sure that if a power failure happens after a store has been accepted to the memory subsystem, the store still happens. It's preserved. Okay, so all you really have to do is make sure that there are instructions for getting things out of that non-part of the part that's not part of the persistent domain. Now, believe me, the first thing I did when I started on this project is I said, listen, I just want software guys to say, store, and it's persistent. And if we could have done that, we would have done that. But it was impractical because, honestly, over the years, the CPU cache sizes have grown huge. And the amount of power that it would take to guarantee that everything in those caches is persistent is a pretty heavy lift. It would take a battery. So we'd basically be requiring every system to have like the motorcycle battery, attached to it. So that's not going to happen, at least for a while. I haven't given up. And so the result here is that of this programming model, if the stores are flushed from the CPU cache and they're globally visible, just to be painfully correct there, then they are persistent. Okay? So the next programming model is the one that we spent more time on because it was more interesting. This is how do you expose persistent memory out of the operating system to an application. So if you've ever saw any talk about persistent memory or the SNEO programming model, you've seen a picture very much like this, but it's all about this red arrow. How do you get this from kernel space up to user space? That red arrow used to be a little higher before we moved it over onto this Mac. And so here you can see the persistent memory at the bottom. I labeled it NVDIMM, and there's some sort of driver or stack of drivers that takes ownership of the NVDIMM. That driver can provide these transparent usages. Now, this is actually a really important point. Do you have to modify your application to use this persistent memory? Not if you don't want to. You can just use it as storage. Look, this file system is unmodified. These applications are unmodified. They think they're talking to a disk because, of course, at the top part of this driver here, it's just the block storage interfaces. Okay, well, that's easy, but that's not really exploiting the persistent memory the way I showed on that latency slide, right? To do that, you take a persistent memory-aware file system. Persistent memory-aware file system, my definition of a persistent memory-aware file system is that it understands the underlying device's persistent memory, and when you open a file and memory map it, you get this arrow here on the right, okay? This means a memory-mapped file gets direct access without using the page cache. There's no paging. If this application does loads and stores, it's loading directly from the media. Right after the initial page faults get the mappings established, there's no kernel code in the data path. There's no interrupts. There's no context switches. It is literally the shortest code path possible between an application and the persistence because you just do a load. There's nothing else. And so if you read we got the SNEA guys together, this sort of work group together, and you'll notice there's no APIs on here, right? Because all I was trying to do is say, memory mapped files. It makes sense. It makes sense. And it sounds kind of obvious now. At least I hope it sounds obvious now. But back then we had all sorts of crazy proposals, right, of new kinds of little persistent memory region IDs and storing them in the Windows registry. I kid you not. So there's all sorts of interesting things. And our idea was just to get a bunch of these OS vendors together. We started this technical work group with Microsoft was there from day one. Red Hat was there from day one. VMware was there from day one. It's chaired by HP and Intel together for a while now. HP is the sole chair of it. There's about 50 companies in it. And if you look in their document, you'll find that the diagram looks almost identical to what I just walked you through. It's basically just getting everybody aligned around this very simple idea that, okay, files have names, files have permissions, memory mapping's been a thing for 30 years. So let's just make it so that when you want persistent memory, you can just use these memory mapping APIs and it should just work. And I'm happy to say that's exactly what happened. So memory mapped files are really the heart of our programming model. And on both Linux and Windows, there's now a term for this idea when you take a file system and you allow memory mapping without the page cache. It's called DAX, D-A-X, short for direct access. And like I say, both Linux and Windows have adopted the same term, although the Windows one has a backslash and never mind. So the last meaning of programming model is the programmer experience. And by this I mean, okay, it's great. If I can just call mmap and get access to my persistent memory, aren't I done? Right? Well, I just told you there's going to be 6 terabytes of this stuff in a 2-socket system. So I call mmap, and suddenly I have a pointer to 6 terabytes of persistence. Then what do I do? Okay, so then what you do is, well, it's up to you. You're free to write your own software at that point, but you're also free to leverage libraries and tools that, that people have put together for you. A few of us got together and we wrote some libraries. We call them the NVM libraries. There's the URL. Our domain name is by far the coolest part of the whole project. But the point is, it's a suite of libraries. There's 6 of them right now. We're about to release a 7th. 3 of them are transactional, and they fit kind of right there. So earlier I bragged, you know, this was the shortest path between you and your persistence. Well, the libraries allow you to put back some common stuff that you might want. For example, an allocator. Something so that you can just say, oh, I want to slice off a piece of my 6 terabytes for this data structure. You know, you don't want to use malloc because malloc will try and allocate DRAM. You don't want to just modify malloc to point at the persistent memory because malloc was written for volatile storage, right? There's no code in the libc malloc that knows how to take a pool that's already been carved up from a previous run and start using it again. But that's what we've put in our library. It is a persistent memory-aware memory allocator. Okay? And so out of all these libraries, if you do plan on going in and playing them, really there's one that you want. It's called libpmemobj for object. By this I mean it's object like an object store, a variable-sized blob. I don't mean object like a Java object. But you'll see it has a lot of features in it. The man page is actually a little too long, but it has atomic operations and transactions. There's actually a cool kind of persistent memory resident lock that automatically releases every time the program crashes or restarts using a kind of a clever generation number based thing, so we don't actually go searching around for locks. There's implementations of things, and there's a bunch of example programs on the website. This library is built on top of this very small library called libpmem, which knows about how to flush things and do the ISA part of the programming model that I mentioned. Okay, so take all those programming models. What is the state of the ecosystem then? This is the culmination of what I've been building up to. The OS detection of the NVDIMMS, again, we already have that already out there in ACPI. It started in ACPI 6.0, and we've been enhancing it since then. How the OS exposes persistent memory to apps. That's a feature called DAX that basically provides the SNIA programming model. It's been upstream in Linux since I think 4.0 or 4.1, so it's actually been there for quite a while. It's gotten a lot of bug fixes and enhancements since then. So the latest kernels are the best, but it's up there. There are 2 file systems that know how to use it right now, ext4 and XFS. More are coming. And Windows, again, they call it the same thing, and right now NTFS is the file system that supports DAX. More may be coming. In our SNIA model, we actually also specify something called optimized flush. This is a optional part of the programming model, which you may or may not implement. This is where you flush directly from user space without any kernel involvement. Today, the Linux support for this is actually evolving. We've hit a few snarls that we're working through. If you use our library and you ask what kind of flush do I have to do, we'll tell you have to call msync on Linux because Linux currently requires that trip through the kernel. Except for this thing called device DAX, which is a special kind of a workaround solution for this problem because we needed the performance of being able to flush from user space. So we're still working on this, but you know, stay tuned to the talk right after mine where you'll hear about the Nova file system that has solved this. And so if you use the Nova file system, user space flushing is completely safe, completely supported, and it's pretty awesome. The Windows NTFS DAX does support the optimized flush. It's completely safe to flush from user space. Remote flush. Okay, so remember before I told you you can DMA to this stuff because it's memory. That means you can RDMA to it, right? The problem is that RDMA only was ever used for volatile memory, right? There's no over-the-wire command in RDMA to say flush something to persistence. There's no option for that. So it turns out that, so that's great, RDMA works fine, but you have an extra step to make sure that the thing that you're sending is persistent if you care. that it's persistent. And that's almost entirely summarized as a second round trip. So for RDMA to do a write, you have to do one round trip. To do the flush, there are many ways to do it, but they all kind of boil down to doing a second round trip. So we're updating the RDMA protocol longer term to avoid that second round trip. So there'll be a new RDMA message that says, the persistence of this data is important to me, so I need to have a flush operation along with this data. So that's coming in an upcoming RDMA proposal. There's another kind of a flush called a deep flush, which we use to make sure that something is in its smallest possible failure domain. And this is not a very common operation, but for file system journals, things like that in the kernel, where you want the file system to be very certain that the data is persistent even in the face of a hardware failure. That allows you to make the file system more reliable, but at the cost of some performance. So we're defining that right now. That's coming out in the next programming model specification. It's already implemented in Linux and Windows. So actually, this is a case where the spec is kind of catching up with the implementation. Transactions, allocations, I already mentioned pmem.io has the libraries that do that, but we're just beginning. It's exactly as was mentioned earlier in the talk from HP. We're just beginning to scratch the surface on this. There's a huge amount that we can do to make this stuff available. We have C, C++, you saw Java, Python support is also on our website, but those things are our first idea of how this stuff should work. You know, as we learn more, as we get further along, I think we're going to learn better and better. And you know, all the transparent usages are still there. You can use it as storage. You can use it as in kernel page cache, things like that. That's all transparent. Apps don't know about it. But to really leverage it, you really want to look at some of this work that we're doing in user space. And then finally, in virtualization, every virtualization technology that I'm aware of is planning to support persistent memory in a guest, so that you can plug some in the bare metal, and the guests will also have access directly, like I drew on the picture with the blue line. Even inside the guest, you'll get that direct load store access. The changes to do this in KVM have already gone upstream. The Zen changes are on their way upstream. And I can't speak for the companies that own their virtualization technologies, except to say, yes, I'm working with them, and yes, it's coming. But they have to tell you the schedules themselves. So if you're more interested in the SNIA stuff that has been going on, the specs and so on, there's this URL here that gets you to all the specs and things that we've been doing. If you, on the other hand, you're interested in trying out the libraries or the language bindings, you can go to this pmem.io site, and on here, if you go look at these slides afterwards, you can see on GitHub here, I put all the kind of URLs to the source. There's the library, the Java stuff. We have an enhanced version of Valgrind, by the way, that helps you find not just memory leaks, but persistent memory leaks, which are particularly nasty. So that is my summary of the ecosystem for persistent memory today.
Great. Thank you, Andy. Questions for Andy? Go ahead.
So you're kind of blurring the line for me between, again, memory and storage. You talked about DACs providing a file system interface. So you have this thing that's on the memory bus that you want to treat like memory, and now you're going to put a file system in front of it, and then you're going to memory map that file system so that you can, I mean, are you going to end up adding layers of?
Only during that's a great question, and only really adding stuff in order to get the permission checking and so on. In other words, we could have invented a new model for how we label the blobs of persistent memory, and we could have then had to invent some sort of permission model for, you know, adding ACLs and owners and groups and stuff. But files have been doing that very well for 30 years. So, you know, while you're setting up the application's access, it goes through all those permission checks. You can't memory map something without opening it. You can't open it without going through the permission checks. So yeah, the software layers are there for that purpose. But then once the memory mapping is done, the file system's out of the picture. It doesn't ever get called again.
Okay, so when you do a load and store, it's not somehow being translated into a read and a write and then back?
No, definitely not.
Okay.
No paging and no traps into the kernel. And you know, again, to be perfectly technically correct, there usually is like an initial trap into the kernel when the mapping first gets set up, like the first time you do a write, you'll take a write fault and the mapping will get dropped in. Those are called minor page faults. They don't have any I/O associated with them, but they just set up the mappings, and at that point, the mappings are there.
Okay, like I said, it takes a while to get your head around all of it.
Yeah.
One other question, do you think that Crosspoint has sufficient durability to be used as memory?
Yeah, that's another great question. I have to be honest, I was combing through the press earlier while I was sitting there to make sure I knew what I could say now that we've done the public demo of it. And I think they've didn't say anything about the endurance yesterday in the announcement. So I have to fall back to what was said at IDF, right? Which is, you know, endurance is much higher than NAND. It's meant to allow you to use it like memory. In other words, you populate your system full of these things when you first build the system. You use the system for its lifetime, which is, you know, what, typically 5 years or so, and then you throw it out. And so it's designed to work in that case. Now, this is an HPC crowd, so if anybody can wear it out faster, it's probably you guys. But for, you know, cloud, data center, the common usages, we expect it to last the lifetime of the system.
So as a Java programmer, the way I can talk to the heap is I can say new of a class, or I can access through something I already have. But if the power went out and now I turn my program back on, how do I, in my program, resurrect from the persistent memory? Is there an old operator, or, I mean?
Yeah, that would be a great idea. So the way it worked is in the Java guys have actually been working with, you know, the people who control Java's definition to make sure what they're doing seems Java-like. And so those classes that I showed you, like sorted map, there are persistent versions of those. And if you have an object that you want to be able to then find again after a crash, there's a thing called an object directory that you add it to. And when you come back up, you can look it up by name. And of course, what's happening, that's at Java, right? But what's happening under the covers is they're just using those libraries that I mentioned to you before, and those libraries are opening up a file on the file system where all the data is kept, and they're calling mmap. So it's all kind of a chain of events that just allows you to get reconnected with what you own.
Okay, so I have to give each object some kind of name.
Yeah, but in practice, what usually happens is there's one or two root objects, and everything else that you cared about persistence is hung off those. So we are not finding people looking up a lot of stuff in that directory. It's usually, oh, let me look up kind of my root data structure for this persistent pool, and then all my data is a tree or something under that.
Okay, thank you.
Okay, one more question.
So the Crosspoint hardware itself, the decay of performance over time, what is that like?
Mostly what I can say is forget everything you know about NAND. Of course, it has its own media management challenges. They have nothing to do with NAND. The performance of this DIMM does not degrade over time. It's the same. The performance numbers that we publish are the same throughout its lifetime. And then there's of course, a management command you can send to it to find out how worn out it is. You know, so it gives you a percentage. I'm at 70% of my lifetime. There are no, you know, long garbage collection pauses and things like that because the media management is just done completely differently. That's one of the reasons why it's a heavy lift to get a technology like this to market.
Okay, sorry.
He's going to cut you off, but I'll be around
If you
afterward.
could talk to him after. So sorry about that. We got to keep. Okay, great. Well, thank you very much.